Work for Europe. Let's go.
So that was a recorded intro from Matt. He won't be here tonight because we have two special guests and our recording software will only allow 4 people at a time. So, Albert.
Good evening.
Good evening. Who we got tonight?
Tobias Hangler and Larrin Thomas.
Hey.
Hey guys.
2 of the most knowledgeable guys on steel, I think, on planet Earth, yeah?
On planet Earth, wow.
I wouldn't push that far. At least not for me.
Well, in any knowledge area, like there's things you know and there's things you don't. You know, I went to college for 8-10 years. I don't know how long it was. And of course, many of my professors knew many things that I didn't know, and I continue to not know them. You know,
Absolutely.
so there's always more to learn.
And then you don't know that you don't know them until you know it.
Yeah, I think that's the part where you start realizing that you don't know anything is when you get deeper into the subject.
So, we got some questions from some of our listeners and people that follow us. I don't know, we can start out with a simple one that Tobias has probably answered quite a few times, but with Apex Ultra, you're using the ESR process to manufacture the steel. And a lot of people wanted to know what exactly is that process and like what are the advantages and maybe some of the disadvantages using ESR besides financial disadvantages.
Besides the cost. Yeah, well, absolutely. ESR means electroslag remelting, and that basically already contains the most important characteristics of the process. Basically, you can imagine it's like you have a block of steel that's called electrode that is hanging from the top, and it hangs basically down into another vessel. And basically in the bottom is the solidified part, and in the top is the starting product. And in between, you have the slag. And the slag is heated by electricity. So that's where the electroslag remelting comes from. And the slag is a very important tool in the toolbox of metallurgy to take certain elements out of the steel and to refine the steel, basically. So whenever you want to take something out, want to take something out of the steel, you have to put it somewhere. And that media is the slag. So if you want to remove impurities, you have to do that, and you have to put them somewhere, obviously. So you take the electrode, you put it in this hot bath of lava, basically, and tiny steel droplets form on the surface of the electrode. And these small surface areas of the droplets allow the steel to be basically mixed with the slag and allow the interaction with the slag much, much better than if you would have just a huge vessel of steel where there's only slag on top. And yeah, that basically is the one part. So you can refine the steel, you can take out so-called non-metallic inclusions of the steel. And the second part is that if you remelt an electrode, you have a more homogeneous structure. So all of these small droplets are pretty uniform, and when they solidify in a very homogeneous way. But if you have a big ingot of steel and you cast that into some kind of shape that is, a big volume of steel that cools down, then the steel does not cool down or does not solidify uniformly, but it basically solidifies some elements sooner, and some elements are pushed into the center of the block of steel where they form segregations. So these can be seen basically in the steel if you etch it. And so the steel in the middle of the block will have a different composition than on the outside of the block. And also in between, there's like smaller segregations and larger segregations. But with the ESR process, you can make these variations much, much, much more homogeneous. So the steel just performs better because it's everywhere the same composition that was intended to be there. That's my short answer. Is that
So
that
you're
understandable?
you're like eliminating more variations throughout a batch
Yeah.
of steel as it gets rolled and pressed and formed to shape.
Exactly. So it's the same everywhere. If you see steel that show beautiful alloy banding or carbide banding, that's very nice to look at in a knife, but it's not the greatest sign for the knife production itself or the processing, because it basically means it's not uniform. There's not the steel hasn't. It has segregated again after cooling down.
So is that making like weak points in the steel when you see something like that?
Well, weak point sounds very dramatic, but let's say the ESR product, a more uniform product, will have better overall performance criteria or better overall performance than a steel that is not as homogeneous, because if your optimum is the original composition, then any segregation means basically you're left and right of the optimum. And left and right of the optimum is not optimal, so it's just not as good. So you have harder spots and softer spots, basically, in an uncontrolled fashion.
Do you know where this method has been developed and when?
It may have been developed in Europe. There's two major methods of remelting. So when Tobias mentioned the electrode, that electrode is a giant steel ingot. So typically in steel production, you have an ingot and then you roll that out. In remelting, you take that ingot and you remelt it. So it gets melted again and resolidified. In this case, in a controlled way to improve the properties. So the other major method is called VAR, vacuum arc remelting.
Right.
And there's even some very specialized steels that will get some combination. Like they'll be vacuum induction melted, then ESR, and then VAR, for like crazy aerospace applications and things. But no, we'll have to Google it for the date.
So is there other steels on the market that are using the same ESR process that Apex Ultra uses, or?
Yes.
Yeah, absolutely. Yeah. For example, Böhler has its nomenclature. Basically, they even produce some steels with ESR and some without. So it's common to have like the deluxe version and the not so deluxe version, so a little cheaper product, and then have the ESR as the improved version of that. And I mean, you always have to look at the whole process chain and then see what comes out the end. It depends on what products you start with and how you treat them. There's like hundreds of parameters of steel production. So ESR is one characteristic that is used in the production process, but it's also the starting materials are very pure, and we try to optimize all of these parameter sets to get the best quality out at the end and still have reasonable cost, of course.
Yeah, usually you know if you're buying an ESR product because it costs more, and so they advertise it as an ESR product.
It sounds like a much more time-consuming project. I'm picturing like a small electrode in tiny drops of steel at a time. That would take a very long time to get a large quantity of steel produced.
Well, at the very least, you're solidifying this steel twice. So, I mean, what industry likes to do things 2 times? So.
Yeah. And I mean, that brings us to the downsides of ESR. Environmentally, we use more energy to produce the same amount of steel because you have to remelt it. Basically, you have to heat it up from room temperature to liquid and then solidify it again. So we put more energy into it. That's definitely something that's not great. But in the end, the product will live longer through that. So we think it's worth it in that case. And another disadvantage is that the yield is a little bit smaller. So, every process step that you do, you lose something between 10 to 30%. 10% might not sound so bad, but if it's 20% and you have 3 or 4 stages in production, it really adds up. And at the end of the day, if you compare the first amount of steel that you put into the ladle to the final amount of steel that we get the bars of steel that we get and that are, sellable, that's not any scraps or anything in between, you're talking about 40 to 60% yield if you have the process that we have. So that's something people are not aware of. But our latest batch, I think, had a yield of 55%, and that was actually really good. It was the best one we had so far.
That was how many tons did you do on that last batch?
I think starting weight was 4.4 tons, and no, I don't have the number exactly, but it's like 3 tons coming out, something like that.
But from what you were saying, you could also do Apex Ultra without the ESR, right? But that would be different steel then, right?
We have been looking at a process that starts a little bit different, and then so right now we start in a conventional furnace, basically having slag and everything, trying to put as many pure materials in there, and then cast it and then remelt it and then hot roll it and so on. A different route would be to start with a vacuum induction melt. So you have less oxidation in the first step, and then you go directly into hot rolling, and you don't do the electro slag remelting. So the question is how similar or how good of a product will it be at the end? And the answer to that weighs 7 tons and is a huge experiment that is slightly expensive. But that's the smallest VIM, so vacuum induction melting furnace that we have in Central Europe. So we've been weighing our options, but we know with ESR the process is very good and very stable. We could maybe get the costs down in certain areas with vacuum induction melting, but yeah, it's an experiment, and we don't know exactly which performance we would have at the end. Is it 98%, is it 100%, or is it like, I don't know.
Yeah, and it's an expensive experiment from what you've been saying.
Yes, quite yes, very, very expensive.
But does the ESR process in the production introduce any risks of failure? So is it a risky step?
Any step in production increases the risk. Just think about knife making. If you do a stock removal knife, there is less risk than if you do forging. Even, if you sharpen a knife, you might have it in your hand, you might drop it. You might, even during shipping, you might ship it to the wrong customer. So the more parties involved, the more production parameters, the more risk. We've had stupid things happen to us, like a total power out while our ingot was remolten. So you just lose like 600 kilos and there's nothing you can do about it in the ESR process.
Mm-hmm.
And
Is that what happened in the first batch?
That happened in the second batch, I believe, or in the second or third batch. It was not, it wasn't a total failure because we still had 2/3 of the ingot, but we lost 1/3 of the ingot. And they don't even compensate for that. They just say, here you go. Here's the scrap value. You get €1 per kilogram, and we don't charge you for this third of the material that we totally messed up. And in the first batch, we had a hot rolling problem. So our heating up curve, holding time, and hot rolling temperatures weren't perfect yet, and we didn't know any better, obviously, because you have to try it. And we did an experiment in small scale, but that does not translate one-to-one to the large scale process, because, for example, solidification times are all of a sudden not 1 minute, but they are hours. So the whole process that the steel undergoes is completely different.
I mean, that every step introduces a certain kind of risk. I mean, that's just logic. But are there steps that are more probable to fail than others in steel production? I know that's kind of a naive question, but
no, I think it's a good question. Is one that's not easy to answer, because I think you would have to be like in the steel works to think about that kind of data, at university we didn't really touch on that subject. I don't know, Larrin, do you have a guess? I don't have any hard facts on this.
Well, there's also two different ways of looking at it. If you talk about a brand new steel product that's never been produced, then there are high risks at virtually every step. Now, if you've got a steel you've been making for 30 years, then, they have yields tracked at every step for 3 decades. And, you can easily answer like, oh, we on average lose 5% here and 3% here, and our worst step is here. Maybe an engineer will be assigned to look at the hot rolling portion of the production or, other parts. But yeah, I don't think there's any generic answer.
For us, the riskiest step is definitely the last step, so hot rolling, or the last big step. They do multiple process steps, but if something goes wrong during hot rolling, we have the most problems because we've already put in a lot of money and work ahead of time. Then if the product fails, basically it's our loss. So that's the step where I'm most nervous, let's put it that way. Because if it happens in the first stage, the company that makes the first stages, they're just going to redo it, and that's it. If it's in the second stage, it's also not as bad, but in the third stage, it gets really expensive. So hot rolling is definitely the riskiest step for us. And we've had a couple of different, minor or major losses during that stage. And there's also a certain risk that they just basically lose a billet because it doesn't hit. A rolling mill is not just 2 rollers, but it's one pair of rollers after the other in the final rolling. So sometimes a bar of steel just decides to go in a different direction, and it doesn't go into the next pieces, into the next pair of rollers, and then it just goes straight out the rolling mill somewhere throughout the building, and they stop the entire process, and then they just cut down all of the pieces that were just being hot rolled, and you lose all of that.
So each set of rollers is reducing to the next thickness. Or...
Yeah, right.
Yeah. Okay. So Larrin, how does that process compare to MacLeod?
Well, MacLeod is made with powder metallurgy, which is a totally different production method. So instead of conventional melting or even the somewhat complicated ESR, there is a ladle full of liquid steel. It goes through a nozzle and then it gets sprayed with nitrogen gas, which rapidly solidifies it into these tiny particles, which is why it's called powder metallurgy. Then they take all of that powder and they put it in a big steel can and they hot isostatic press it. It's called hipping. So under high pressure and temperature, sort of similar to how you forge weld Damascus even, only it's millions of tiny powder particles. Then that creates an ingot, which is, 99% dense. And then they roll it out, which removes any remaining porosity that might be present in the ingot, though it's already, 99 point whatever percent. And then it gets rolled out. So otherwise pretty similar. It's also on a pretty small scale, maybe even smaller scale than the ESR. A few thousand pounds is a single hipped ingot.
So after that, all the processes are the same when you're rolling and reducing everything to bar size.
Right. Then you anneal it and you cut it up and you ship it to customers. So powder metallurgy, what's great about it is, Tobias talked a lot about homogeneity. Powder is the most homogeneous steel product available just because everything solidifies so rapidly. Things can only segregate within that tiny volume that becomes that little particle of powder. So in general, powder metallurgy steels have the best homogeneity, the best uniformity, and very small carbide structure.
Because of the increased surface area, I imagine, right? Of each.
And also the solidification rate. So,
yeah, the solidification is the major part. If you've got a giant ingot that is solidifying over hours or even days versus a powder that cools, almost instantly, it's just totally different orders of magnitude.
Basically, there's no time for diffusion. So the elements, they always seek the most comfortable spot. And if they have lots of time, they segregate, and so they separate from each other, and they form areas that are concentrated with more manganese or something like that. And those would be visible later if you etch it. And if there's only a tiny droplet and it has a fraction of a second to solidify, then the elements can't go really far. It's the same, or it's a similar thing with heat treating. So if you have your steel austenized, all the carbides are in solution, and then you quench it, there's no time for the carbon atoms to move in the solid state, to go anywhere. So they have to form martensite. But if you give them a lot of time, cool them down slowly, then they will go out of the matrix and form carbides instead. And if you give them a lot of time, there's going to be big carbides. You give them a little bit less time, the carbides are going to be smaller, and the steel is more homogeneous.
Yeah, and these aren't just like nerdy things interesting to metallurgists. When you measure the toughness, like impact toughness, you break something. If it's made with powder metallurgy, it is more difficult to break. It takes more energy to break. And so, having a homogeneous, fine microstructure leads to better properties. And in the case of MagnaCut, the steel probably would not be possible to produce using conventional methods. You would forge it and it would just break apart.
That's what I was just going to say. That's usually the criteria where the industry decides to go to powder metallurgy. Nobody does it for fun, but usually you go to powder metallurgy if you're making steels that otherwise would form such terrible large carbides or segregations that you can't just produce them in a conventional method. So now you can put in more alloying elements and go through powder metallurgy, and it still works out because of the process, because there's no time for making large carbides. So if you go to a certain amount of carbide volume, it just makes sense to go to powder metallurgy. Whereas if your alloying composition is, let's say, 50 to 100, so you have only 1% of carbon in there, it doesn't really benefit the steel if you do powder metallurgy, or at least not even closely enough to justify the costs.
Yeah, so Apex Ultra was designed with conventional production limitations in mind, or maybe ESR, where MagnaCut was designed with powder metallurgy in mind. And so there's different ways you design the grades for those different limitations.
Could you make Apex Ultra also with powder metallurgical methods?
Yes.
Or wouldn't that make sense?
Yes.
Okay.
Yeah, you could, but it would make it 3 times more expensive.
Yeah, sure.
So,
we'll make Apex Super Ultra someday.
I think that totally works out. It's a good brand name.
But how old is this technique of powder metallurgy?
It's been around for a while, but industrial production has probably, I don't know.
And
Larrin, do you have
1970.
numbers?
Yeah, 1970 is when commercial production started at Crucible Steel.
So is it an American invention then?
Yes, it was followed shortly after in Sweden by a company called Stora. They started doing it shortly after. Of course, they claimed that their invention of it was independent, but there were court cases and, lawsuits but
okay.
We don't need to get into that, but yeah, it was started in America. So USA. Oh wait, this is a European podcast.
Yeah.
So I had from the Hustle and Grind podcast today, Ryan Chadbourne was talking about something interesting. He said that he uses cold bluing on carbon steel before heat treating to eliminate and reduce decarb. Have you guys ever heard of anything like that, or is that even possible?
I haven't heard of that one specifically, no.
I think I heard about it, but I haven't tried it, to be honest. So, I mean, any dense layer that slows down diffusion can have an impact on decarburization and oxidation. I definitely say it's possible. I don't know the exact composition of cold bluing solution or what it forms. So in general, my answer is it's possible. I haven't really looked into it too much because for me, at a certain point, Scalex works really well, easy to apply, and that just answered my necessities that I had. And on most of the blades I grind away at least 0.2, 0.3 millimeters of each side of the bevel after heat treatment. So I'm not worried about the decarburization in my normal production method, just the way I have my process laid out.
Yeah, so you mentioned Scalex, and we talked before about a couple of people having like spots showing up on the blades after using Scalex. So in the US, Larrin, I think Scalex is equivalent to Condor. Is that the name of it?
Condorsal, I think.
Condor.
Yeah.
Yeah, there's a range of different scale preventing commercial products out there. So, I mean, some of these guys get creative with different coatings or things, but I mean, you might as well start with the commercial products. I don't know why you'd, I don't know. Don't get too creative. Somebody else has already thought about this.
Yeah.
And cold blowing solution is also not cheap, at least not here. It's quite
That's
expensive.
what I was thinking. It's more expensive than
Scalex.
Yeah.
Yeah, that's true.
No, but I had a knife with the same. I mean, I sent you pictures before, Tobias. It looks like small little dots and spots on the blade afterwards that I had to get rid of. And for me, I think that that the spray hadn't dried completely. That was the problem. It went into the oven, and there was some spots that weren't completely dried, and they kind of shrink and shrivel up and made those little circle dot areas. So if anybody's running into those problems, that's probably why.
Yeah, I also give it 2 light coats, not one thick one, and let it dry in between. That usually works really well. And I only do it if I want to protect the surface, basically. So as we talked about, like engravings or, I don't know, just if I want to finish the knife pretty much before heat treatment and go to a finer grit for some reason, then I will use Scalex to reduce oxidation. Also on stuff like punch marks or stuff that you don't really touch after heat treatment, just to make sure that the surface doesn't oxidize too much.
Yeah, I will just add, I sometimes see confusion from knife makers between scale and decarburization.
Yeah.
So lots of times I'll get a question like, "Oh, my knife is reading 45 Rockwell. Why didn't it harden?" And the first thing to suggest to them is just to grind off more and test it again. They say, "No, there's no scale on it." But scale and decarb are two different things. So the scale is the oxide layer. Oxygen and iron, it's making an oxide, and you can see it. It's black, maybe brown, and it comes off. And underneath that is a layer of steel with no or very little carbon in it. You can sometimes see that, sometimes it's slightly discolored, or if you etch it, you can see where that layer is. But often it's invisible. It just looks like steel.
And that's the best test. If you etch it, it's like a cloudy area that doesn't etch correctly.
Absolutely. I mean, it even looks really good on forged blades sometimes. If you leave it close to the spine, it looks like you have a laminate, like a Sanmai or Gomai. But it usually etches bright, whereas, at least if you have a dark etching steel anyways, then you can see it on the outside. And if you forge your blades and you don't forge a blade in 20-30 minutes and have your... even if you forge it in 20-30 minutes, there's going to be decarburization on there. And if you take 2 hours to forge a blade, then there's definitely going to be a lot of decarb on the surface of the steel. So, same thing, I always recommend grind a little deeper, and then you will see if you have full hardness.
So, Albert, did you get any questions from some listeners or some of your own questions?
Not from listeners, but I'm super interested in how the development of a new steel starts, because from what I've heard, you can't go directly to a huge steel mill and have them produce 7 tons. This wouldn't make sense. But how do you get an idea of the ingredients you'd like to try for a new steel, and how does the first batch look like? I'd suppose you would do a small batch at the start, How do you do that, and where do you do that?
Yeah, sure. It's a great question. Basically, everything starts with the idea, just as you mentioned, and once you have an idea of what you are lacking, usually, so there's this steel that's pretty good, but it's not quite what you want, and you want to change or improve on some characteristics, then you start thinking about other steels that maybe have one of the other attributes that or one of the other characteristics that you're looking for, and start comparing and start basically researching and if the steel that you're thinking of or that you're wishing is even possible, or if the two things are not alignable, if they can't work out. And then on Apex Ultra, we started with thermodynamic simulations to see which phases the steel would form if we had a certain composition. So you play with the alloying elements, basically we want a little bit more carbon hardness, carbides, whatever, and then you think about what that will do to the steel. So which carbides do you take? Do you take more vanadium, more tungsten? And you try to interpolate the data that you have from other steels to point you in the right direction of the new steel. And that's where Larrin's wealth of knowledge of testing has been invaluable for developing Apex Ultra, because we had lots of data all done in the same or in a very, very similar setup, and they weren't data from different steel mills using different norms and different machines for the same testing. So that was really cool to have that all done in the same house, and we could look at these data and then decide on the new composition of the steel. And once you have your theoretical optimum, if you have your simulations and your designed composition, then you go and make a small laboratory melt. So that was in fact a vacuum induction melt. So that was the process that I was speaking about earlier. So in the laboratory testing, we had a vacuum induction melting, not an electro slag remelting process. And now you're only talking about 10 to 20 kilograms. But the steel is still going to behave similar to what you're going to have if you scale the process up. Just a little different. So we cast this, I think it was 10 kilos of an ingot, of which we could use like 3 or 4 kilos. And then I just basically threw it in the forge and tried to simulate the process of forging and hot rolling the steel into a bar. And then we made a bunch of different testings of heat treatments and characterized those again with Larrin's testing method to see how it would compare to all the other steels that he has been testing in the past. Anything I missed, Larrin?
Well, yeah, I mean, you missed everything. I mean, it's impossible to distill things down. You know, it depends on exactly what you're making. You know, what you're looking at properties you want to achieve, but it's impossible to have maximum hardness, maximum toughness, maximum corrosion resistance, maximum forgeability. You know, you can't get every property all at once. So there's all these trade-offs. You know, and so Apex Ultra, it tilted towards we want a forgeable grade that has higher wear resistance and high achievable hardness compared to other forgeable grades. And so a lot of times at that point, you start looking at microstructure, like Tobias said. So we wanted harder carbides in there. We used a combination of chromium enriched iron carbides and tungsten carbides and vanadium carbides. And so we're not just adding elements willy-nilly and seeing what happens. We are trying to achieve a specific microstructure. So in that case, we wanted those 3 carbide types, and we wanted them basically to dissolve by the forging temperature to improve forgeability. So that's one of the things we're looking at. Then there's also hardenability. Is it going to be a water hardening steel? Can it do a hamon? Is it an oil hardening steel? So there's so many properties that you're trying to balance, and that's just for Apex Ultra. If you're looking at a different steel, then there's a whole different set of trade-offs that you're considering.
So are there, did I understand you correctly, that you run simulations? Is this like computer simulations where you put in the elements and then the computer simulations calculate how the final structure is going to look like? Or
it's a combination. So I mean, Apex Ultra, it is a combination of the Japanese blue super steel and 52100. And so we already knew from practical experience and looking at those steels what its microstructures look like. And so we combined those two things together. And ThermoCalc, or the simulation software, really just allowed us to narrow down some things. So typically, we might say, okay, how much carbon do we need for those carbide forming elements? We're not sure. We'll do 3 melts of vacuum induction melting at 3 different carbon contents. Well, with the simulation software, you can put everything in there and okay, this carbon content should do it. And you can reduce the number of iterations that you need to try. Only rarely can the simulation software tell you exactly what to do. So you have to have ideas and things to try, and then you can punch them in the software and see if it leads you in one direction or another. But of course, the simulation software may also be wrong. So it's a blessing and a curse.
Yeah, at some point you just gotta throw some money at it and give it a try, see what happens, right?
Mm-hmm. Absolutely. Yeah.
So did either of you, Larrin or Tobias, have failures in your steel? Like you thought you had it all figured out and made a test batch and it didn't come out the way you expected?
Actually, with Apex Ultra, we were pretty lucky with the first melt. We were pretty much spot on with what we wanted with the first melt. So we did a good due diligence ahead of time. But there was, there's all of the little problems that we were overcoming. Like, for example, the melt had a huge lunker. There's Larrin, help me on this. What's the English name when the melt falls in at the top and just forms a void that goes down all of the way in the ingot?
I think that has a technical term that I cannot remember. I'm not a steel making metallurgist, so I don't remember these terms. So we'll call it a big hole. Oh.
We'll call it a big hole. We had a big hole going basically 2/3 of the ingot down. That was why we could use most of it. And that's, for example, one challenging characteristic of Apex Ultra. Its processability in the steel making is not super easy, which, basically also increases risk, increases cost of production, but we think it's worth it, and it's working out now that we have figured out the production route, basically.
Are you present when a new steel batch is made?
Not in all stages. I have been at all companies that are involved in the production process, but I haven't been present at each company at each time. No, that would be too much.
How many companies are involved in a steel like Apex Ultra?
It depends. At the hot rolling, or at the product that everybody knows now, there is one company casting the ingot, another company remelting the ingot and heat treating the ingot, and the last company is basically separated in a couple of smaller steps. There's pre-rolling, then there's the final rolling, then there's heat treatment, then there's sandblasting and straightening and commissioning. So there is basically 3 large companies plus all the shipping involved in between. With the new product, so the 2.5 and 3.6 millimeter sheet metal that we are currently producing, there's actually 5 companies involved. Because we have, it's a little bit more of a complicated process because of the intersections between the companies. So we're trying to make a small batch of a steel in a process that's laid out for very big production processes. So it's a little bit more complicated. So we have one casting, one remelting, one forging, one rolling, and one cutting. So it's 5 companies.
Holy shit. I always thought it's way easier. You give them the recipe and they do all of it and they ship you like 7 tons of steel. But that there are so many companies involved. It's interesting.
Yeah, basically it's a specific thing because we are still placing small orders. So our last order was 6 tons, and you're still barely scratching the minimum of these companies. So, for example, Böhler's minimum batch for doing the entire process all by them is 12 tons.
Okay.
And we simply don't have the money for that.
But Böhler could do all of it if you ordered 12 tons.
Could do all of it, yes.
Mm-hmm.
And you told me before you're also kind of at the mercy of the production companies when they do things in certain steps and certain batches, and if you don't get your steel or a certain step of the steel finished at the right time, then you might have to wait a couple of months before they get all the machines and the tooling and everything set up to do the next step, right?
Yeah, it's ridiculous. Especially in the beginning, they just tell you, yeah, you're last in line, and we'll do this whenever we feel like it. Now it's getting better. Now it's getting towards a healthy relationship, giving and taking. But it's also, when we did the first batches, it was the economy was booming. The steel industry was at its maximum capacity. And some of the companies gave us 24 months lead time. So it's like, yeah, come back in 2 years.
Yeah.
But now it's a lot better. The whole production process is a lot nicer because we order more and they have less work. So that puts us in a better situation.
Do you have to take care of all the logistics? Do you have to say,
Yes.
Oh, shit.
Every step. They don't do that for us. So I'm spending a lot of time with all of the shipping and the coordination.
I can imagine, yeah.
It's fun.
Is it though?
No, no, it's
No.
not fun. Not at all. Shipping a knife is already bad. Shipping 6 tons of steel is a nightmare. Yeah, if I had a truck, I would just drive myself.
So we got, now that we talked about the technical term, a hole in the steel that I mentioned, we got a couple of questions from users of both knife steels with questions that they have about steels or impurities. I guess we'll start with Larrin's with MagnaCut. It's been kind of big talk right now on YouTube and the internet everywhere, with some people having decarb and like voids and stuff in the steel. Is that like a manufacturing process error, or I mean, I know there's a whole lot of stuff in the background that's way out of your guys' hands. Can you tell us more about that?
About that. So almost all of the rumors come from a single man. So he owns a controversial knife company. This company is controversial because he has taken pre-orders several times and not delivered knives. More recently, he bought a bunch of MagnaCut and he sent it to the heat treater. And the heat treater did a stress relief process in air. And they believed that they either wouldn't have decarb or not enough to worry about. Well, this knife maker, he did not leave enough material to remove after heat treating, especially not for this stress relief in air rather than under vacuum or other protected atmosphere. So he was very upset about the decarb on the surface of the steel, and he went to Niagara, who hot rolls the steel after Crucible makes the ingots, and he demanded, refunds for all of the steel. The steel is still good, it just has decarb on the surface. They told him no, and then he started threatening that if they didn't give him the money that he wanted, that he would start making videos about how terrible Niagara and Crucible are. So a couple of months went by, and then he started doing that. Multiple videos per week, sometimes multiple per day, about how you shouldn't do business with Niagara. And then he started making videos saying that he had voids and inclusions. So what to say about that part? So, it's hard to tell where they are coming from. More recently, he did a video where he showed what direction flaws in the steel should be based on the rolling direction, because he's cutting out his knives perpendicular to the rolling direction rather than parallel to the rolling direction, which is more typical. And he drew on the knives the direction that the flaws should be based on the direction he's cutting them out. And then the flaws he showed were all in the wrong direction. So he seems to understand that they're supposed to be in the rolling direction, but then none of his are in the rolling direction, which is just a roundabout way of saying that the flaws cannot be in the steel. They have to be showing up in his process. He's creating them. So, of course, no steel is perfect. There's always going to be some a level of inconsistency in the material. But he was claiming a 20% defect rate from the steel, which is just way too high. And so anyway, his flaws come from his production process. You can tell because they don't follow the rolling direction. I'm sure MagnaCut isn't 100% perfect. Maybe 1 out of 1,000, 1 out of 10,000, who knows? Knives might have a tiny flaw in them from some, combination of factors in steel making. But, this guy's got a vendetta against Niagara. He has said so in his videos. He wants people to not go to Niagara because he's mad that they're not giving him. I think the most recent number he gave is he wanted $250,000, even though he's never purchased that much steel from Niagara. So I showed pictures of the defects in his knives to knife manufacturers like Chris Reeve Knives. They've used more Oh, I should also mention, he started with MagnaCut, but then he started talking about all Niagara steels and all crucible steels. So it wasn't limited to MagnaCut. He doesn't like all CPM crucible steels. And so I showed pictures of the flaws to Chris Reeve Knives, who's used, almost more MagnaCut than anyone, and they've been using CPM steels for 20 years. And he said he'd never seen flaws that looked like it, which again likely indicates it's a difference in processing rather than a steel issue. So from what I can tell, these claims of, voids or imperfections are not true, but it is very annoying. So, I mean, he keeps making videos and tagging me in them and trolling me on my Instagram. And then I blocked him, and then he made videos about how mad he is about being blocked. And so it's very annoying.
Yeah, difficult situation. But it seems like all those problems are showing up after the heat treating process. Like none of his knives or the steel that he's gotten have been tested beforehand for voids or anything. They just show up.
No,
after a third party is heat treating and cutting them out.
Yeah, he's been saying he's going to do, ultrasonic testing or something to find voids, but he's not going to find any. So most often when you get an imperfection in steel, it's actually more common in conventional steels because of the segregation. They've got carbide stringers, and sometimes those break out when you're grinding or finishing, and you get a tiny imperfection. Well, often tiny, sometimes bigger than tiny. But that's not because there was a hole in the steel. It's because, there is a microstructure feature which broke out during grinding. This is a powder metallurgy steel, so those are very rare. And then the other term he used was inclusions. And again, that's easy to misconstrue because all steel has inclusions in it. We always talk about like how many inclusions or what volume fraction of inclusions, because they're always there. And I think he's implying big, giant inclusions, which would be very uncommon. So they're always present on a very small scale, microstructure scale.
What's an inclusion on a molecular level? What is that?
Yeah, so the most common are like, Tobias mentioned earlier non-metallic inclusions. So very common ones are sulfides and oxides. So that's when there's oxygen present in the steel and it forms with something else. Or sulfur, the reason why we add manganese to steel is because a manganese sulfide is not as bad as an iron sulfide. Iron sulfides are very bad. The steel will be ruined during hot rolling. But manganese sulfides, they are more ductile and they will elongate during rolling rather than just fracturing in the steel. So sulfides and oxides are the most common inclusions.
And they built during the production process of the steel? Or
yes.
When are they forming? Okay.
And so we try to minimize them, but we can never entirely eliminate them. So there's always impurities or inclusions in the steel. We try to get as few of them as possible and to keep them as small as possible. But most of the time, they don't create issues. It might be that a cleaner steel like Apex Ultra made with ESR is, 10-20% tougher than one with a higher inclusion content. But generally, they don't show up as, macroscopic features that you see with your naked eye.
Mm-hmm.
That's
rare. And you add certain elements to the steel to minimize the inclusions. Did I understand you correctly there?
To modify them into better inclusions.
Ah, okay.
I mean that's probably the best example you can give with iron sulfides and manganese sulfides. If you have ever tried to forge steel that's meant for machining with additions of sulfur, then you know that it just crumbles at a certain temperature and it just falls apart even without impact. So it's iron sulfides are liquid, and then the steel crumbles apart.
Yeah,
but if you add manganese, it's better.
There are some elements added to deoxidize the steel. So common ones are like titanium or aluminum. And so they'll form oxides in the steel, which will float up and become part of the slag, which is then removed. But again, you can't get rid of every single oxide that's in the liquid steel. But you try to minimize them.
The slag prevents oxygen from getting into the steel?
Also,
yes.
Okay. The slag is a wonder weapon. It's great for everything. You can add elements to it. You can remove elements from the steel into the slag, and it prevents oxidation. So there are various different slags throughout the steel making process, and it's like a whole thing. There's industries behind making synthetic slags. It's not like it's a byproduct that's worthless, but it's like steel manufacturers actually buy designer slags to add to the steel to get the right slag for the right process step for the right steel, and so that you can take out and put in the right kind of stuff into your steel.
Ah, cool. What happens to the slag as soon as the steel's done, finished? Is it waste?
It depends on the process step. We try to make as many byproducts out of whatever we produce, right? So we try to modify the slag in a way and cool it down in a way so it becomes a type of gravel that can be used in construction or in, for example, street manufacturing, street construction. It goes with the asphalt. I don't know what's the right term for that, but yeah, different slags have different uses. Let's put it that way.
But you can't reuse it in steel manufacturing.
Some you can put somewhere else, and you can reuse parts of the slag again in the same process. But at some point, it's tired. There's too much of something in there. There's too much oxygen. There's too much sulfur, whatever, in the slag. So then you have to remove some and add a fresh one. There's also projects to basically try to purify the slag again and then reuse it. But it doesn't always make sense. Sometimes it's just, now it's gravel, it's good, and use it for somewhere else. I mean, usually it's limestone and stuff like that, silica sand. So it's nothing super toxic or expensive. It's just some dirt, designer dirt.
Yeah.
So Tobias, you're up next with Apex Ultra. We had a couple of questions from our listeners also about Apex Ultra and the thick decarb that forms after heat treatment. Have you run into this same situation or problems? Or
I mean, it's a high carbon steel, so it does have a high activity of the carbon in the steel, and you definitely see that when you lose some carbon and the steel changes in its properties. We have seen let's say a little bit more pronounced decarb layer on the second and third batch of the steel on the bar surface, and we were trying to look into that with the process metallurgists of the hot rolling, because there's different temperatures and furnace settings and heat treating parameters. And we also did an experiment to see if we could minimize the decarb by grinding off a certain amount of steel from the surface after the intermediate rolling before the final rolling. But it turned out that didn't change anything at all, really. So we concluded that the decarb must happen afterwards in the process. So it must be from heating, final rolling, or heat treatment, and from these parameters, the final heat treatment is the most likely because the product is only 5 millimeters thick instead of being 10 centimeters thick before hot rolling. And the hot rolling is basically just one hit. So as we said, we have roller after roller after roller, and they just reduce the stock down from 10 centimeters to 5 millimeters, for example. And that's just a few minutes, and then it's cold again. Anyway, so it is a hot rolled product, which means it has had it has had contact with the air during rolling, and then we have to anneal the product. So we have to make it soft enough for cutting, right? And in the last batch, I haven't really done any microscopic testing or anything, but just in the processing myself, I feel like by narrowing down the heat treatment parameters, by giving them less room to play with in terms of time and temperature, we've reduced the problem, and the decarb layer actually got a little bit better. This is never going to be zero unless you grind off after hot rolling, which would reduce the yield a lot, and I don't think that's worth it because costs go up, yields go down, and as soon as you throw the piece of steel in the forge, there's going to be decarb in the forge anyways again. So yeah, that wouldn't make sense.
Yeah, I think these listeners were talking about thicker decarb after they forged the knife to almost.
Actually, after forging. Right. To be honest, I couldn't say that I see it more than in any other steel, but I've worked a lot with 52-100 and 125-62 in the past, so I think these steels are kind of in a similar range of alloying composition, and it might be different. I mean, if you forge a blade out of ADCRV2, for example, and not out of Apex Ultra, then the steel moves a lot faster, and I will need less heats to achieve the same degree of deformation, or to forge out the same blade, basically. Maybe that's part of it. I don't know.
I mean, Albert, you work a lot with Apex Ultra as a core steel. Have you noticed anything similar? Or?
Yeah, we've noticed something similar, but I wanted to ask you something else because I've made 2 Apex Ultra blades last week, and I had dots after etching in the gray part of the blade. So we made blades with 200 layer Damascus on the outside and Apex Ultra core, and I had dots, and I could not get rid of them. And I've never had this before, so I might have screwed up when forging.
It could be overheating in that case.
Yeah, that's what I thought.
Especially when you're laminating, you're always pushing the temperature up, right? So you're like, I could do 1150 is gonna be fine. But if you go a little bit too high, then you can mess up the steel, and that could show up in points. Curious to see what Larrin's theory is, but it's one of the most common mistakes. I get a lot of, what did I do wrong? I have cracks. What did I do wrong there? And usually it's overheating during forging, cooling too fast after forging, or basically not sealing the weld when forge welding.
Yeah, higher carbon steels are more sensitive to being overheated. So a lot of knife makers that are used to working with ADCR-V2 or other simple steels will be heating just as hot as when they work with those, and that's likely to lead to issues. And also, sometimes people think, oh, this is a high carbon steel. This one's going to be tough to forge, so I'm going to go hotter. Or in the case of laminating, like you said, like, oh, I need to make sure I get a good forge weld, I'm going to go hot. And but if you go lower temperature and soak longer, you're likely to have better success.
Yeah, just stay below 1150.
I mean, we usually do because we have a thermocouple inside our forge. To be honest, I left the blade sitting in the shop for 3 or 4 months, so I had surface rust on the core section of the blade. So I thought that it might have something to do with that. Because it was really rusty, to be honest. It was not just surface rust.
that could also happen, but that also means you probably have no recollection whatsoever with the forging temperatures.
No, but with Apex, we're super careful usually, so we run the forge with.
I mean, you make a lot of steel, so obviously you have the process down. It can just be small fluctuations.
We usually very sensible or careful when it comes to temperature. Especially with Apex, because we've also ruined Apex.
Yeah, haven't we all?
So might it have something to do with rust? If the blade gets rusty before I finish and etch it, that the deep rust might show
pitting
up.
corrosion can go pretty deep, and it can be points. I haven't seen the blade, and I don't know how much you took off afterwards.
Yeah, not much. I mean, it was right before hand sanding. I ground the blade, I left it in the shop for months, and then I started hand sanding, which was a pain in the ass, by the way.
Oh, come on.
Yeah, I think corrosion would be the most likely explanation
pitting.
in that case.
That sounds like pitting.
Okay.
Yeah, one thing I've seen with MagnaCut, people try to darken it with ferric chloride. And,
that's good.
And all it does is pit. It never darkens. So I get pictures of MagnaCut with giant pits in it.
Yeah, that's another thing. If you want a corrosion-resistant steel, make it shiny and make it polished, and don't make it dark, because anything that's dark is already an oxide, so it's a starting point for corrosion.
Yeah, another knife maker, he had been used to using CPM 154. And he'd treat the steel by putting it in a foil bag, but not sealed. He would leave the foil bag open.
So you can grab it with the tongs.
No, he did it just so it would form black oxide on it, so it would form scale.
Oh, really?
So he started using MagnaCut doing the same thing. And he got a picture back from a customer where the edge of the knife had just totally folded like a potato chip, because there was no carbon left in it.
Decarb.
And so,
Shit.
So I tried to talk to him about when you put it in a foil bag that's open, the foil doesn't do anything. But he was very upset with me. So.
No. Yeah, you're wrong. He's using foil, so it's good.
Yeah,
he's using foil, so it's good.
Why was he using foil? I mean,
I don't know, because he thought he was getting some perfect balance. He's getting the black oxide that he wants, but it's somehow protected. But no, it's not protecting anything.
I mean, from a kinematic, or it's probably happening slower.
Mm-hmm.
Let's give him that. But it's not worth it.
Yeah, so what the foil does is, so you've got it sealed up, and there can still be oxygen in there. But as the foil heats, it's so thin that it heats up first, and it oxidizes so that it sucks up the oxygen that's in the bag. And so if there's just air going into that foil, then the foil cannot do very much. So.
No.
So there's no need to put small pieces of paper
No.
Yeah, I was going to ask that.
No, you don't
I
need
used to put like cigarette papers in my foil to burn up the oxygen, but it doesn't actually change anything, right?
No, you don't need that. It just gets extra junk in the foil bag with the knife. I have heard some people say when they have sticking issues, like the foil welding, that when they put powder
Baby
or
powder,
whatever,
Graphite. Yeah.
that it helps prevent the sticking. I don't normally have sticking issues, but so I mean that could be a reason to put something in there.
But usually the foil blows up somewhat, so there's no. I always use foil unless I use X scale, but the foil, usually the envelope you build usually blows up anyway, so there is no sticking issue. I've never had any sticking issues unless with MagnaCut, because the temperature is so high that I might have used the wrong foil. So the foil was treated to 1,200 degrees Celsius, and that was too close for MagnaCut. So the foil was all soft and stuff, and this was the only time the foil stuck to the blade.
Interesting.
Yeah, the foil is rated to 1,200 degrees, I believe.
Yeah.
Albert?
Yeah.
And MagnaCut, you need like 1,100. Is that
I think
right?
it was 1,150 degrees Celsius. But we have an expert here, Larrin. What's the hardening temperature for MagnaCut?
Well, it has a pretty wide hardening range. The datasheet says that the baseline midpoint is 1120 Celsius. But because primarily what you're dissolving, well, first the chromium carbide dissolves, but that's below 2,000 degrees or 2,050 degrees Fahrenheit. So, 1,100 Celsius or so. And then after that, you're dissolving more vanadium and niobium carbides, and they are much more stable. So the hardening range is actually quite wide, at least 100 degrees Celsius, depending on your final hardness target. So stainless steel can be easier to heat treat in some ways.
So I might have went for the middle temperature then. With 1,000.
That would be my guess if you were trying it for the first time. But I don't know if that's an issue with the foil, or just like you said, at higher temperature, the welding may happen more readily.
So I had another interesting question. Some of these I've never heard of from a listener. He was asking about forge welding, and he asked what works best, borax, WD-40, diesel, or quenching oil. I've never heard anybody using quenching oil or WD-40.
For forge welding, Apex.
Yes. Well,
Yes.
just any steel in general.
Any steel in general. Well, we have to make a differentiation between which steels we're talking about. In general, for example, if I make Damascus out of 15 and 20 and 128-42, so let's just say these are the classic Damascus combinations that probably in the US have very different names. 02, I think, and 15 and 20, right?
1084 and 15 and
1084,
20.
thanks. Yeah. Then you don't really need a super seal. You can do a dry weld with the right burner settings, so you don't need any of these. If your gas forge and your burner settings are slightly reducing or neutral. Slightly reducing is the way to go. So you have a little bit more gas, your flames are a little bit longer, you have slight blue flames out of your gas forge, and you need a good mixing of the gas and the air before they hit the burning chamber. Then you have just less oxidation because there's more fuel than oxygen, so the steel will not oxidize anyways. So that's how I do my dry welds on on, let's say, simple steels. So steels with little content of chromium and silicon and stuff like that. Anything that oxidizes. But if you go to steels like Apex Ultra or 15 and 20, 50-100, they have a little bit of chromium in them. So then you need something else. And then you might need a flux or you might need to weld them shut at all sides. So to go back to the questions and the proposed methods, I would put diesel and quenching oil and WD-40 all into the same category of, if your burner settings are right, you can use all of them. They will all burn because oil does not exist at 1150 degrees. It just burns away. So by the time your entire billet is heated up to the full temperature, there's not much left of the oil anyways. So just make sure that you have a somewhat pure oil that doesn't include any additives that would still exist at that temperature. I don't know, some...
Yeah, the WD-40 and those oils burning off, like they can remove oxygen as long as they're still...
As long as they're there.
They're still burning. So, I mean, if you've got a sealed canister with a little bit of that oil in there, it can burn out the remaining oxygen. If you've got an open billet, eventually oxygen can get in. And borax is a totally different thing. A flux eats away the oxides and removes them, so that then you have steel contacting steel again instead of an oxide in the way, so that they can weld. So they're totally different ways of doing it.
Of working, yeah.
So they're all basically just making like an oxygen barrier to a certain temperature.
They all try to remove the oxygen. So you want two
Okay.
metallic surfaces touching each other, and there are various different ways of achieving that. One is burn more fuel than air, and you have less oxygen in the mix.
Mhm.
One is, add an oil or graphite powder or whatever, so there's more carbon, so there's more fuel to the air that's touching it. Until it's all burned, then it's all away. So it doesn't form like a permanent layer. It just helps to reduce oxidation. And if you have borax on there, you have your liquid melt. It's basically a slag. So it prevents oxidation, and the oxidation that has already happened by then is dissolved into this ceramic liquid. And my favorite method is just don't let any oxygen in there. So if you have two surfaces that are flat, you put them together and you seal the entire thing, either with heat treating foil or with welding everything around it, then there's no air inside. So I don't need to worry about oxidation, and then I don't need to worry about getting the borax out of the billet again, because that's the downside about borax is you have borax in between your layers, and you have to be careful to squish it back out. It has to go somewhere, and it should be in your knife after you've done all the forging.
So if you don't get all the borax out, is that something that's visible in the steel? Like,
Yes,
is
very
there
visible. It's a bubble,
Oh,
because the borax doesn't go anywhere. If you have
So
a
it's a-
little bit of oxygen in between two layers, and then you forge them down from 40 millimeters to 10 millimeters, it's going to stretch out and it's going to be absorbed into the steel, basically. Which is not great, but it's not visible, at least, to the naked eye. But if you have borax, it's going to stay in there, it doesn't go anywhere, and then you grind into your blade and you have a borax bubble.
So that's what, when you see a delamination in Damascus, that would most commonly be a borax bubble.
Possibly, yeah.
Mhm.
Any more questions?
Sure.
Albert, do you have any? I got
Go
one
ahead.
more, but you should go ahead.
Have you guys heard about people oil hardening steel between copper plates? Have you tried this, or do you know anything about this? Is this fast enough for an oil hardening steel, copper?
It depends on the steel, first of all. So not oil hardening steels are the same.
Yeah.
And it also depends a lot on the geometry of the knife. So it also comes down to your process. If you're making 5-6 millimeters thick stock removal blades and you quench them in between these plates, the cooling rate of the cutting edge, of the future cutting edge, is very, very different than if you have a 2 millimeter stock. So I'm going to say that if you have a 2 millimeter piece of Apex Ultra that's entirely flat and you press it in between two steel, aluminum, or copper plates, you will harden the steel for sure. because Apex Ultra has a relatively high hardenability. So that means it hardens relatively easy, even at slower cooling rates. So it's a combination of factors. It depends on your steel. It depends on the thickness and the geometry of your knife. So did you pre-grind your bevels? Are they at full thickness? If you pre-grind your bevels, it's the plates are probably not touching the edge, so they can't remove the heat.
Yeah, but let's suppose it's a flat piece of steel.
Yeah, if it's a flat piece of steel, then just the thickness matters, basically. And then
but is the final hardness going to be as high as with oil then?
Depends on... copper is actually a really strong conductor, so I'm going to say it's achievable. With thin blades and 2 copper pieces, everything clean, I say you achieve full hardness with Apex Ultra.
Cool. Mm-hmm.
So we should point out that sometimes you can get full hardness or near full hardness, but there can be pearlite that forms, so carbides that form during the cooling if it's not fast enough, and that will reduce your performance. And I've even seen cases where, a high carbon steel came out very hard, 65, 66, 67 Rockwell, but there was a little bit of pearlite in there, and that affected the edge performance. So it can be a little bit worrisome if you can't check with microscopy to make sure that you're getting the right microstructure at the end. I would be worried when I compare 2 different oil quenchants and one gets me 66 Rockwell and one gets me 63, a knife maker might say, 63 Rockwell, that was good enough, I just won't temper as much. But that 3 Rockwell difference probably comes from undesirable transformations.
So.
Okay. Mm-hmm.
So basically, quench as fast as possible and as slow as necessary, not to get cracks and warping.
Mm-hmm. I have no intention of using copper plates.
No, I wouldn't even say it's a bad idea for... I don't know, if you have a production process focused around, petties or folders and stuff like that, we would have to test it. And I'm not even sure if you really have slower cooling rates in the upper temperature than using oil. If you use enough pressure and if your metal-to-metal contact surface area and the heat transfer is good. So there's a lot of ifs, but I think it can work from just watching even the press dies suck out heat out of a gigantic billet. We all know that metal-to-metal surface contact is pretty strong. The oxide layer in between can be a problem. Any layer can be a problem that slows down the heat transfer. But I personally love my quench plates, but I use oil first and then I go into the quench plates.
But is it copper quench plates or
no?
I
even use steel because for me they are mostly for
keeping the blade straight.
Keeping it straight, yeah. So I go down to the martensitic transformation temperature. So let's say 140 degrees Celsius, and then I go out of the oil and into the steel plates and clamp the knife to keep it straight.
Tobias's quench plates are in his press.
30 tons pressure. Yeah.
Yeah.
Really?
That'll keep it straight.
I also have some in a vise, and it's enough, but you do see a slight difference. I have some in the vise because it makes it easier for students, and I teach a lot of bladesmithing classes to do it themselves. But when I do batches, I put them in the press.
And what's the difference? What's the difference between the
power? So
the power.
Press, the press just keeps them a little bit straighter.
Okay, really? Okay. That the final straightness is different. Okay.
Yeah. Also, speaking of distortion, I've had some really cool feedback from makers that I haven't really realized so much myself, but that Apex Ultra monoblades are really dimension stable during heat treatment, and that people have like the best results in terms of keeping stuff straight that was either machined or ground before. So I found that quite interesting. I don't realize it so much because I've changed my process so much ever since I've basically entirely switched to Apex Ultra. But it's it's cool. It's cool to hear. Do you have any experiences like that, Albert?
Apex Ultra mono steel plates. So, or
Yep.
no?
I guess anything laminated doesn't really count because.
No, I haven't. But do you have an explanation why this might be? Might this be due to the ESR process used in Apex Ultra? Do you have an explanation for?
It will depend on the production method of the alternative steels. Many of the sheet metal production steels will be coiled.
Mm-hmm.
So then, they roll it down I don't know, 2 meters wide, and they coil it up into a big coil, obviously. So the steel basically cools down in the coil, and it decides, okay, I'm a radius now, so I want to be like this forever. And then they uncoil it. So in the cold state, they bend it back, make it straight, cut it, and the steel has some, let's call it, the steel remembers.
A memory.
A memory, thanks. My English gets worse as the day goes longer. The steel has a little bit of a memory effect, and when you heat it up again, it slightly flexes back into its original position. That, and also it depends a little bit on the alloy composition and the basically also hardenability and how homogeneous the steel reacts. Quite simply put, a water quenching steel will always be more prone to warping because you need to quench it really fast, and any area of the steel that doesn't get exactly the full quenching speed because of an air bubble, because of your movement of your hand, because of the spine thickness or whatever, is not going to harden the same way as your edge did. And that creates differences in the blade, and that creates tension, and tension leads to warping.
Mm-hmm. No, but we've never had any issues with Apex warping more than other steels, or less. I mean, we only use it in laminates, so we've never done a Apex Ultra mono steel blade.
I've done like 2, and then I decided that hand sanding is a bitch if you do mono steel.
Wow,
it's not worth it. So I just keep my cutting edge, small, have the cladding thick.
Yeah, we do that too.
That gives you the best of both worlds.
Yeah, because when we were we do mostly Damascus on the outside and Apex as a core. And we only use hardenable steel for our, like the standard recipe for Damascus on the outside. So this gets also pretty hard, right? But when you hand sand an Apex Ultra laminate, all the scratches on the cladding, they disappear, but they stay in there on the cutting edge. But it makes for an awesome.
It makes for a better blade. That's for sure.
It's an awesome steel. I mean, we've dropped Apex Ultra blades on concrete and everything, and nothing ever happened. Even they might have been lucky.
No, it's fucking ridiculous. It's our baby, but I wholeheartedly love the steel, and it doesn't. I feel the difference compared to all of the other kitchen knives that I still have, that are not out of Apex Ultra. You can feel it when you use it, and you can feel it when you hand sand it, that there's a significant difference to other low alloy steels.
Yeah, and even when sharpening, I mean, holy shit, it gets so sharp and so fast. I mean, that's all. That almost sounds contradictory, right? It gets fast. It gets sharp so fast, but with Apex,
if you have fine edges, it's a joy to sharpen.
Yeah, it is. Yeah.
Awesome. Good to hear.
Keith, do you have another question?
Just in regards to the warping issue, as soon as you start with some kind of a laminate, all the effects have to do with the outside jacket material that you're using.
Yes. So especially if you're using something that's not a hardenable steel. So I would always say, like, if you have Apex Ultra in the core and ADCRV on the outside, they behave somewhat similarly, so you can do anything with them. You can basically treat them as a mono steel during forging, during heat treatment, and so on. You just need to make sure you grind until your Apex Ultra is in the middle. And you can even do cryo treatments, because the two steels behave very, very similar. But if you have something like wrought iron or austenitic stainless steel grades, these have different microstructures. They have different characteristics of elongation and contraction when you heat them up and cool them down. So then we have problems with stresses and warping again. So they can be a little bit trickier in terms of production. And you need to be more careful.
Not only with the heat treat, but grinding afterwards. If you're doing a post-heat treat grinding, you can get warps in it just from the stainless steel jacket, like pulling on the cold material more to one side.
Pulling. I mean, it's the same with decarb. If you have, on any steel, if you have a thick layer of decarb, that's a ferritic steel, basically, steel layer. So when you grind off the decarb from one side, the blade or the billet or whatever just bends away from the surface that you just ground. I'm sure most people have seen this before. And then you grind the other side, and all of a sudden it's straight again. You see, the best visibility is on the surface grinder. If you have a surface grinder, you put the steel on there, you remove like 0.3 millimeters or something, and then you take it off, and it's like entirely bent. If you put it back on, the magnet sucks it down, it's straight again. You grind off the second side, and you take it off, and it's perfectly straight. It's magic.
You're also fighting with the force from the magnet. The magnet will hold the blade straight even though it's bent. And you grind it down, and then it bends back the other way.
Fun times.
Fun stuff.
Do you recommend cryo treatment with Apex?
In general, yes, if you can. It's not strictly necessary. It makes a fantastic blade without cryo treatment. But if you have an option to cool or deep freeze or cryo, then use it. I oftentimes, especially in the bladesmithing classes, I only use the freezer and not the cryo treatment with liquid nitrogen, simply because liquid nitrogen always has a certain risk of cracking blades. And even just a layer of decarburization can be enough to rip your knife apart. So if you're making a class, you want to go home with a knife, and I don't want to have split blades. So we might lose a few % of performance if you don't use cold treatment, but in general, we get fantastic results with just using a freezer. That also just is me being consistent throughout the year with my final temperature, if that makes sense.
Yeah.
So in summer, the outside temperature might be 30 degrees, 40 degrees in the shop. And that way it's always minus 20. I always have the same end temperature, summer and winter. Even
with stainless claddings on the outside? No, okay.
Don't do that. Also not
that's
with
what I thought,
wrought iron. Yeah,
okay.
So if you have wrought iron, if you have anything ferritic or martensitic, then don't do cryo. Just go cold treatment. Cold treatment is always safe. I haven't had a single blade crack in the freezer.
And freezer, we're talking minus 20 degrees Celsius? Or,
yep.
Okay.
Yep. Household freezer.
Yeah.
Yeah, so I do have another question, but I want to talk to Larrin about his new book that he's got out now.
You mean the story of knife steel?
That's the one, yeah.
Yeah, so
how's that going for you?
So that book has been going great. The book is about the history of steel, but it's also the history of knives in modern times. So, from 1900-ish to today. So, 1900 is roughly the dividing point for when metallurgists began adding alloying elements to steel. So before then, basically everything was simple carbon steel, iron and carbon, maybe a little bit of a couple other things like manganese. So they started adding alloying elements to steel and figuring out new exciting ways of designing steels that happened around that point. And so I tell the whole story of how the metallurgists figured that out, what alloying elements to use and when, all the different steels that were developed. So if you want to know where different steels came from, all the way up to MagnaCut, I have it in there. Which companies designed them, and even better yet, which metallurgist when I can find it. Lots of old advertisements, And then I also covered the history of knives, primarily in the USA, for the manufacturing companies, and then what led from those like inexpensive pocket knife companies to the high-end production companies that we have now, starting with companies like Gerber and Buck. Then coming out of those were companies like Benchmade and Spyderco and other ones you've heard of. And then where the custom knife industry came from. How did it explode in the 1970s? Explode in a good way. And the major custom knife makers that contributed to the craft and design and, of course, the popularity of different steels. So one famous one would be Bob Loveless with 154 CM and ATS 34. Another one would be Bill Moran with Damascus. But so there is some stuff from Europeans as well, like Manfred. His last name I can't pronounce, Saxa, in Germany. He was making Damascus before Bill Moran. He came from a tradition of German Damascus makers. So cool stuff like that. So I got to interview a whole bunch of knife makers and Damascus makers. And so the book is huge. There's tons of pictures. And it tries to tell a story, like it says in the title. So the story of how things happen. Why did people decide to do things? It's not just dates and facts. You know, I don't care about such and such war occurring on this day. You know, what matters is the story of the people that decided to do things. So I try to have firsthand accounts, you know, interviews with people or historical interviews when, you know, they're no longer alive for me to interview.
Going back that far in time, before the internet, it's probably a lot of discrepancies where one maker claims that they were the first to use this steel. Or...
Yeah, there were tons of those. So where I could, I tried to track down who was first, but, you know, many things were not recorded. So when I could, I just said, you know, like this maker says he started doing this on this day, and this maker says he started doing it in this year, and this maker says he started doing it in this year. And sometimes I might also add, but this maker was the most influential one who popularized this thing. You know, so, you know, if one obscure knife maker does something before other people, but nobody knows about it, you know, does it matter? You know what I mean? So, you know, if a tree falls in a forest, but no one hears it, doesn't make a sound, you know, so.
That's kind of like the Gold Vein Project, Tobias, huh?
What are you getting at?
We could save that for another podcast, though.
Yeah, that's true. That's true.
So where can we find that book, Larrin?
Yeah, you can get it on Amazon in most European countries. If not, there's also a PDF that you can get through a website called PayHip. So if you go to my website or just type in the story of knife steel and go to the page on knifesteelnerds.com, there's a link to the PayHip site where you can get the PDF. So you can get paperback, hardcover, or the PDF. The hardcover is a way to go, but it's expensive and takes longer to get it. The paperback is pretty nice. And it's, you know, half as much as the hardcover. If you've got a nice iPad, you know, the PDF can be a good way of reading it. But yeah, so that's what I would.
I love the paperback. I think it's more comfortable to hold.
Yeah, I mean, I prefer reading books, you know, in print, you know, physical printing. And when I have tried buying books digitally, they just sit on my phone or my iPad, and I never go to them because when I get on my iPad, I browse the internet or watch YouTube or something. I don't think.
Yeah, there's too many distractions. Yeah. I have the book too. I got it for Christmas.
It's a great Christmas present.
Yeah, my girlfriend asked me what I want to have for Christmas, and I sent her an Amazon link.
Good idea.
Yeah. No, I really enjoyed the book. What was fascinating for me is that today steel development seems to be very systematic, right? Mm-hmm. So we know how different elements interact with one another, and from what we've heard, there's even simulations and stuff. But back then, at the beginning, like let's say 20th century, the beginning, it used to be a lot of trial and error, right? So they made a steel and they made tools out of the steel, and then they gave it to the fabrication shop or to the guy on the lathe, and they were just testing the steel in the field, right?
Yeah.
So that was super interesting to me, because nowadays this seems to be way more systematic on how people develop new steels. I mean, it's not a surprise; it's the same in every science.
Yeah, the very earliest alloying experiments, people in England were bringing in Waltz from India. And they were like, wow, this steel is better than what we're making here in England. How can that be? We're the smart English, And so they're trying to copy Waltz, and they decide, well, maybe they're adding special elements. So they do these experiments where they're adding crazy elements that we don't even use today, like palladium and silver and things, and just trying it. And that's basically what things were in the 1800s. Just, we're going to throw in this element and see what happens. It might not even mix into solution with the steel. You might just have palladium floating around in the iron. So that's the source of where the term silver steel came from, though, is their favorite in those experiments was adding a tiny bit of silver, even though what we call silver steel doesn't have any silver in it. That's the origin of the term.
Mm-hmm. Interesting. It sounds a lot like alchemy.
Yeah, I mean,
throw together all these things, and then you just test the steel and see how it performs.
Yeah, that's basically what it was. Oh.
Yeah, but some parts or some elements of this are still present to this day, right? So when you guys were telling us how you developed Apex Ultra and how you tested it, the testing parts seems to be similar, right? So of course we have standardized tests today, but still you can't predict the properties or the performance of the steel just with simulations and the recipe, right? So you have to actually test the steel then.
Yeah, simulations only get you so far. I find that toughness is often the least predictable because you cannot perfectly control the microstructure. If you've got a large carbide or a large impurity somewhere, your toughness is bad. Or you accidentally overheat the steel and you have a large grain size, your toughness is bad. But there are trends. So, the more carbide is in the steel, the less tough it is. You're approaching the toughness of the carbide itself. So there are things you can predict and there are things you cannot. So ultimately, you have to test it and see what you get.
Do you think that there will be some point in the future, a time where we can predict all these things with computer simulations, also toughness and stuff?
No.
No, okay. Because it's too complex.
Yeah, I mean, our simulations get better all the time. My job at US Steel, we wish we could predict every property, but we can't. And part of the problem is, there's a lot of talk about artificial intelligence and AI models right now. But a lot of data about steel is not public. It's locked up within the steel companies. The steel companies may not even have a, rigorous, systematic database of all of their information. Some of it is only locked into people's heads or reports that someone wrote it or in a filing cabinet somewhere. So an AI model can only be as good as the data that you put into it, and the data is not there.
Okay.
So if we had an infinite amount of data, then we could have perfect models. But our data is limited and will remain limited for the foreseeable future.
Yeah, so I got one more question. I had a listener that has an Apex Ultra core with wrought iron cladding, and he would like to know from Tobias what your recommended etching process would be. He's using GatorPiss. I don't know if you've used that yet.
I have it sitting there. I haven't actually used it. I'm excited to use it, but I want to document it well.
Don't get too excited, Tobias.
Are you not too excited? I heard it's selective and slow, and that's it's fine. Just depends. Depends on what you want. I always basically use two etching solutions or concentrations. I have an aggressive etching solution that's like ferric chloride 1:5, 1:10 approximately. In that I do all of my deep etching. So if I want to have a physical contrast of the heights of the layers of Damascus, I use that. Just eats away the dark steel. If you want to have a more pronounced edge on the Apex Ultra with wrought iron, you can give it maybe 5 minutes in the ferric chloride first, then rinse it off, neutralize it, and then I come to the second stage, which is more selective, a little bit more subtle. And at the moment I use 40 degrees Celsius warm orange juice. So it's an orange juice edge. It's similar to basically a coffee edge, but in my experience, in my process, it doesn't turn as brownish, but it gets a nicer black without the brown tones. And 42 degrees has been my optimum temperature for speed and contrast for most of the steel combinations that I use. And yeah, if you don't want to temper, if you don't want to heat up the orange juice basically, then you can simply wait longer. Just put it at room temperature overnight and you will have a nice edge. Although, to be honest, I've had very nice edges on wrought iron by just dunking it for 2 minutes in ferric chloride and then rinsing it off and neutralizing afterwards. It all depends on how much of a contrast you want. Do you want the apex to be fully darkened? Do you want it a little bit more subtle? Which finish are you going for, basically? So I don't think there's a one-fits-all answer to this question, but these are kind of my approaches of thinking. The ferric roughens it up a little bit, gives it a little bit of depth, the edge, and then I wash it off, neutralize it, and then I put it into a slower, more selective edge to get a color contrast from the different steels.
Albert, you've worked with wrought iron cladding before, right?
Yeah, we did it with coffee.
Yeah, coffee works.
We did
very, very similar.
Because we couldn't get the orange juice method to work.
It depends on the brand and temperature.
Yeah.
My recommendation is the orange juice from Lidl, I believe, Solevita.
Okay.
In the 2-liter pack, not the bottle. That's the best.
I bought the cheapest orange because I'm cheap. I bought the cheapest orange juice I could find on it, and it didn't work. It was the one from Clever.
From Clever. Yeah, I had problems with. I think I tried 3 or 4 until I was happy. But there's pros and cons. If you have good results with coffee, just stick to the coffee. But I got brownish tones every now and then, and that wasn't.
Yeah, we do too. But it also depends on the brand of coffee. We use the Nescafe, I think it's called dark or strong roast or something like that. Mm-hmm. So the instant coffee. But I'd rather have something else because the coffee, that's always messy.
It's always messy. One advantage of the coffee is it holds up a lot longer than the orange juice. You have to throw away the orange juice after about a week.
Okay.
4 or 5 days. So yeah, if you work in batches, not a big problem. It's €2 for 2 liters or something like that, and then you can etch your blades and it's good. But if you do one knife and then in 4 days the next knife and then it's already broken, it's not working anymore, then it's a shame.
Mm.
I mean, yeah.
Now I'll give the orange juice another try. Yeah.
And what's your experience with Gatorpiss? I'm interested now.
Yeah, it doesn't work for us.
Okay, but
and we've been.
From what I understand, it's similar to a coffee etch or something, right? So it's slow. It's a color contrast thing.
There is this video by Baker Fortune Tool on YouTube, and where they explain the whole process. They say 600 grit finish. We even do 1,200 or 1,500, but they say 600 is plenty. So 600 grit finish, degrease it, put it into Gatorpiss for 20 minutes at room temperature, take it out, perfect contrast. If we follow these instructions, it doesn't do anything to the blade.
Really?
Yeah. So we leave it in the Gatorpiss. So what we do now is we do 3 cycles in ferric chloride, and then we put it into Gatorpiss for darkening, but for, I think, 2 hours, 1 or 2 hours at least. Because if we do less,
temperature plays a huge role.
Yeah, but it's
you know that, right?
Yeah,
so
yeah, sure. But it's we also tried heating up the Gatorpiss with a Tauchsieder, But and we try to hold air bubbles as generating air bubbles with a pump and stuff, but yeah, nothing worked for us. But
Interesting.
yeah. Well, so we're back to coffee again, and now hopefully orange juice if I can find a Lidl somewhere. So
Just give it a try. Maybe it works.
Thanks for the tip.
Yeah, no problem. But it's a lot of trial and error. I try to keep everything as consistent as possible, and it changes. I have a sous vide stick,
Yeah.
They're pretty cheap now, and I have basically a big pot of water where the sous vide stick sits in, and then I put my vessel with the orange juice or the coffee inside the water bath. So I'm heating the water. Otherwise, if you try to heat the orange juice directly with the sous vide stick, I'm not the best at cleaning everything all the time. Sometimes I get stuff, and then your sous vide stick. Yeah, your sous vide stick sucks. So yeah, that's how I do it, and that way you can get very consistent temperatures on the edge, and at the push of a button.
Yeah.
It's not a big deal anymore.
But what I really like about your guys' processes is that they're so precise. You can tell me that the degree your orange juice is at when you're etching the mask. I mean, no normal knife maker can do that. Yeah, it's at 23 degrees or whatever. 40 degrees. Of course, and that's actually a lot of help for other knife makers, right? Because that's easy to replicate. Because room temperature is a vague term. What's room temperature, vague, right? Yeah. So, but that's awesome. And it's also very beneficial for our listeners, I think, because now they can just copy your process and hopefully get good results.
I hope so. Absolutely.
That's great.
One thing about the grits that I often encounter, which grit to send to. If you want a really dark edge, especially if you want to darken out a monosteel blade, for example, or you just want a really dark edge on your nickel Gomai blade, don't go crazy high on the etching, on the hand sanding. I generally recommend something around 800 as well. Baker, you said, is recommending 600. 800 is plenty, because if you go to 1500, 2000, whatever, I know it's not a lot of work, so you can do it quickly, but it actually makes the edge less stable in my experience. So I prefer something like 800 and then the ferric and then the orange juice, and then I'm happy. And that makes a very stable oxidized layer.
I mean, we usually go that high up if we want the nickel steel to really shine. Yeah. That's why we go that high up. But if we do an edge, a dark edge on a monosteel blade, we usually, 240 is enough, right? So, but is it due to the increased surface area with the coarser scratches, or what's okay?
Basically,
that's
just
the reason. Okay,
it can grab onto it.
Yeah,
and also vice versa. If you want to have a polished blade that is as corrosion resistant as possible, polishing it up, making it as fine as possible actually helps form less corrosion. So the blade will have worse corrosion resistance at a 60 grit than it will at 1000 grit. A freshly ground blade after water grinding, it rusts in 2 minutes.
Yeah.
It's insane.
Yeah.
I've tried the fish tank bubbler thing with gator piss before, and it pretty much turned everything black. I don't know why it does that, but it's just the introduction to oxygen, I guess, over the surface of the blade.
But now that's interesting, because it's somewhat contradictory to what Albert just said. Because now you're saying that the etching potential is pretty high, it's pretty aggressive. I'm curious to try it out myself. I have to try it out myself.
No, what I said, it didn't work. So
said it didn't work, but not that it
we did not get the nice contrast Baker Fortune tool got, because Baker Fortune, they put it in there for 20 minutes, they take it out, it's silver and black.
Yeah.
And that didn't work with no method. So
yeah, time is only a constraint if it is for you. For me, during the classes, time is a big thing because I want to have the etch done within 30-40 minutes during our lunchtime. So etching time for me is very important to get a good finish in the classes. But if I am not doing classes, but I'm doing batches, then I'm just grinding one knife after the other anyways, and then, it doesn't matter if the first knife sits for 2 hours. So, yeah, it just depends on your process.
You need a consistent and reliable etch for the classes.
Absolutely.
Hey guys, we are almost on to 2 hours right now, and Larrin has another commitment today. Maybe we have time for one more question if Albert has something. Other than that,
No, I'm good.
you're good. You learned everything you needed to know?
No. But that's always the case. You never know enough, right? And
Student's mindset, that's good. Yeah.
If Larrin or Thomas have a plug or anything they want to add to the conversation, now's the time.
Well, I still have a
Larrin,
website
keep me quiet.
and a YouTube channel and an Instagram.
Ooh.
They're all called Knife Steel Nerds, so you can go check out those. Buy my books. I'm always doing more steel experiments. It's never ending. I'm working on annealing of stainless steels right now, and so that's been fun. Since not very many bladesmiths work with stainless, I'm trying to answer some of the questions on that front. So, and I'm doing a Woot study and CPM1V K888, which is a new steel. What else am I doing? Also, there's a Chinese knife steel called ARRPM9, which is supposed to be an exclusive powder metallurgy steel, but it's looking like it's probably not a powder metallurgy steel. So keep an eye out for that. Lots of fun things coming.
Awesome. Well, for anybody who doesn't know what I do, I teach a lot of bladesmithing classes. So if anybody's interested in that and want to see and do my process hands-on, you're very welcome. Just sign up to the newsletter, and whenever there will be new slots available for the classes, you will get an email. And other than that, we make laminated steels, mostly from Apex Ultra. And you can get some of them, for example, at knifematerial.at. Also, if you need a little bit more of a steel and it's something that it's not available at Knife Material, you can just send me an email and see if we can make that for you. We have a nice rolling mill, so we can roll everything out to the thickness that you want. Yeah, and we also do other stuff, but yeah. That's good enough. Classes and steel. Knives. Also knives. Yes. All right. Thanks, you guys.
Yeah.
Thanks a lot for having us, for being patient and sticking around for 2 hours of nerdy talk about steel and inclusions and holes in the steel.
Yeah.
Thanks for inviting me.
Thank you both for being on the show. We'll have to listen to the episode a few times to let everything sink in, and go buy the story of knife steel. Buy one for yourself, for your friends. Send them out as gifts, and
also buy Larrin's other book. The knife
both
engineering
books, multiple
book.
copies. Yeah, knife engineering.
Yeah, buy as many as you can.
Mm-hmm.
That's like the best shop reference book. You just buy one for the shop, and it's got dirty fingerprints everywhere, and buy one for the coffee table.
Yeah, knife engineering is really a good wealth of information.
Yeah,
it's a good basis for
an awesome resource. Awesome. Yeah. We call it the Bible in our shop. We have two.
That's perfect.
Thank you.
Very good.
It's also my first source of information whenever I have a new steel that I'm playing around with.
Yeah.
Perfect.
But make a version with metric, Larrin, with Celsius and stuff. Because
the first few weeks, the book was primarily Fahrenheit, and then I added Celsius basically everywhere in the book. So if you have a really early copy, it's primarily Fahrenheit. But
yeah, it's almost all in Fahrenheit.
Yep. Mine has both in there, not everywhere, but most of it.
Mm-hmm.
See, I was an early adopter.
Yeah, I guess you have to buy another copy. Oh, well.
There you go. All right, guys. Thanks again.
Yep, bye-bye.
Thank you.
We'll talk to you all next week. Bye.
Bye.
Bye, guys.
Bye.